This is SpaceTime Series 19, Episode 93, for broadcast on the 28th of December 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, new findings provide more clues about water habitability on Mars, icy surprises on Rosetta's Comet, and a new explanation for the so-called alien megastructure star. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Water probably existed on the surface of Mars in conditions that would have been suitable for microbial life to have thrived if life existed on the red planet. The new conclusions are based on the discovery of boron on the surface of Mars by NASA's Curiosity rover. The findings, presented at the American Geophysical Union Conference in San Francisco, provide new clues about the potential for long-term habitable groundwater in the red planet's ancient past. If the boron discovered in calcium sulfate mineral veins on Mars by Curiosity is similar to that seen on Earth, it would indicate that the groundwater of ancient Mars that formed these veins would have been at temperatures of between 0 and 60 degrees Celsius with a neutral to alkaline pH. This temperature, pH, and dissolved mineral content in the groundwater of Mars could have made the planet habitable. However, the environmental implications of the boron found by Curiosity are still open to debate. At the moment, scientists are considering two possibilities for the source of the boron left by Martian groundwater in mineral veins. It could be that the drying out of part of Gale Lake could have led to the formation of a boron-containing deposit in an overlying rock layer not yet reached by Curiosity. Now, if this is the case, then some of the material in this overlying layer could have been carried by groundwater down into the fractures in the rocks where Curiosity is now looking. On the other hand, it could be that changes in the chemistry of clay-bearing deposits and groundwater affected how boron was picked up and dropped off within the local sediment. The boron was identified by the Curiosity rover's laser-shooting ChemCam instrument, which was developed for NASA at the Los Alamos National Laboratory in conjunction with the French Space Agency. The discovery of boron is only one of several recent findings about the composition of Martian rocks, which have been made by Curiosity as it climbs up the side of Gale Crater's central peak, Mount Sharp. The Martian mountain was chosen as the target for Curiosity's mission because of its geologically layered structure, a feature which would allow scientists to read the geology of the region like a book. The six-wheel car-sized rover is finding rock composition evidence of how ancient lakes and wet underground environments changed billions of years ago in ways that affected their habitability for potential microbial Martian life. As the rover's been progressing uphill, scientists are finding that the compositions trend more towards clay and boron. These and other variations are providing geological clues about the conditions under which the sediments were initially deposited, and about how later groundwater moving through the accumulated layers altered and transported the ingredients. Groundwater, and the chemicals dissolved in it that appeared later on Mars, left its effects most clearly in mineral veins that filled cracks in older layered rock. But it also affected the composition of the rock matrix surrounding the veins, and the fluid was in turn affected by the rock. NASA lead scientist John Grotzinger from Caltech, the California Institute of Technology in Pasadena, says there's a great deal of variability in the composition of rock at different elevations. He's described it as hitting a geological jackpot. As the rover moves further uphill, researchers are impressed by the complexity of the lake environments when the clay-bearing sediments were being deposited. They're also impressed by the complexity of the groundwater interactions after the sediments were buried. Grotzinger likes to describe a sedimentary basin like this as a sort of chemical reactor. Elements get rearranged, new minerals form and old ones dissolve, and electrons get redistributed. Now, on Earth, these reactions support life. Of course, whether life existed on Mars is still unknown. When the Curiosity rover first landed in Mars Gale Crater in 2012, the mission's main goal was to determine whether the area ever offered the sort of environment in which microbial life on Mars could have existed. And within the first few months of the mission, the answer came back with a resounding yes. In fact, the more research Curiosity does, the more interesting its findings become. 4 recent drilling sites, spread about 25 metres apart in elevation, are allowing scientists to sample progressively younger and younger layers as Curiosity moves uphill. This uphill pattern's allowing the science team to reveal more of Mount Sharp's ancient environmental history. Gerasimenko says the variations in these minerals and elements indicate a dynamic system interacting with both groundwater and surface water. The water influences the chemistry of the clays, but at the same time the composition of the water is also changing. Gerasimenko says this chemical complexity indicates a very long interactive history with the water. And he says the more complicated the chemistry is, the better it is for habitability. The boron and clay underline the mobility of elements and electrons, and Gerasimenko says that's good for life. You're listening to SpaceTime. I'm Stuart Gary. The European Space Agency's historic Rosetta mission to the Comet 67P Churyumov-Gerasimenko may be over, but scientists are still making new discoveries as they sift through the petabytes of data collected during the journey. The Rosetta research team have just discovered that as Comet 67P approached its most active period back in August 2015, the spacecraft spotted carbon dioxide ice, never before seen on a comet, followed by the emergence of 2 unusually large patches of water ice. The carbon dioxide ice layer covered an area comparable in size to a football field, while the 2 water ice patches were each larger than an Olympic-sized swimming pool and much larger than any previous signs of water ice detected on the 5-kilometre-wide comet. The 3 icy layers were all found in the same region of the comet's southern hemisphere. The combination of the double-lobed comet's complex shape, its elongated path around the Sun, and the substantial tilt of its spin means seasons are spread unequally between 67P's 2 hemispheres. When Rosetta arrived in August 2014, the comet's northern hemisphere was still undergoing its 5.5 Earth-year-long summer, while at the same time the southern hemisphere was in the midst of winter and much of it shrouded in darkness. However, shortly before the comet's closest approach to the Sun, perihelion, which was in August 2015, the seasons changed, and the southern hemisphere experienced a brief but intense summer, exposing this region to sunlight again. In the first half of 2015, as the comet steadily became more and more active, Rosetta observed water vapor and other gases pouring out of the comet's nucleus, lifting its dusty cover and revealing some of the comet's icy secrets. In particular, on 2 occasions in late March 2015, Rosetta's visible infrared and thermal imaging spectrometer found a very large patch of carbon dioxide ice in the Unhor region of the comet's southern hemisphere. This was the first detection of solid carbon dioxide on any comet, although it's not uncommon in the solar system. For example, it's abundant in the polar ice caps of Mars. Scientists have long known that comets contain carbon dioxide. After all, it's one of the most abundant gases in cometary atmospheres after water. But it's been extremely difficult to observe CO2 as a solid ice on the surface. You see, in the cometary environment, carbon dioxide freezes at minus 193 degrees Celsius, which is way below the temperature at which water turns to ice. Now, above this temperature, carbon dioxide sublimates, changing directly from a solid into a gas, and hampering its detection in an ice form on the surface. In contrast, water ice has been found on many comets, and Rosetta has detected plenty of small patches of water ice in several regions of 67P. The CO2 patch, consisting of a few percent of carbon dioxide ice combined with a darker blend of dust and organic material, was observed on 2 consecutive days in March 2015. In fact, it seems the team may have lucked out, because the CO2 ice was gone when they looked in the same region again 3 weeks later. Now, assuming that all the carbon dioxide ice had turned into gas, scientists estimate that the 80 by 60 metre patch probably contained about 57 kilograms of carbon dioxide, corresponding to a 9 centimetre thick layer. The research team say its presence on the comet's surface is likely to be an isolated rare case. In fact, they believe that the majority of the comet's carbon dioxide ice reserves are confined to far deeper layers inside the nucleus. This icy patch probably dates back a few years, to when the comet was still in the cold outer reaches of the solar system, and its southern hemisphere was experiencing its long winter. At that time, some of the carbon dioxide still outgassing from the interior of the nucleus would have condensed onto the surface. There it would have remained frozen for a long time, only vaporizing when the local temperature finally rose again in April 2015. This discovery reveals a seasonal cycle for carbon dioxide ice, which evolves over the comet's 6.5 Earth-year orbit around the Sun. It's all quite different to the daily water ice cycle detected by Rosetta's instruments shortly after its arrival at Comet 67P. Interestingly, shortly after the carbon dioxide ice disappeared, Rosetta's OSIRIS narrow-angle camera detected two unusually large patches of water ice in the same area, between the southern ridges of Amher and Bez. Scientists had already previously seen many metre-sized patches of exposed water ice in various regions of Comet 67P. But these new patches were much larger, spanning some 30 by 40 metres each, and persisting for around 10 Earth days before they completely disappeared. These ice-rich areas appear as very bright portions on the comet's surface, reflecting light that's bluer in colour compared to the redder surroundings. Here on Earth, scientists have experimented with mixtures of dust and water ice to show that as the concentration of ice in them increases, the reflected light gradually becomes more and more bluer in colour, until eventually reaching a point where equal amounts of light are reflected in all colours. The two newly detected patches contain 20 to 30% of water ice mixed with a darker material, forming a layer of solid ice up to 30 centimetres thick. It's thought one of them was likely lurking beneath the carbon dioxide ice sheet revealed the previous month. On a global scale, the research team found that the entire comet's surface turned increasingly bluer in colour as it approached the Sun. This happened because the intense heat caused vaporization, lifting off large amounts of dust and exposing more and more of the ice-rich terrain underneath. And as the comet moved away from the Sun, scientists observed that the overall colour of the comet's surface gradually started turning redder again. They also revealed local variations in colour, indicative of the daily cycle of water ice. Quickly turning into water vapour when exposed to sunlight during local daytime, it condensed back into thin layers of frost and ice as the temperature decreases after sunset, only to vaporise again the following day. This distribution of water ice beneath the dusty surface of the comet seems widely but not uniformly spread, with small patches punctuating the nucleus appearing and disappearing as a result of the comet's activity. Occasionally, larger and thicker portions of ice are also uncovered, dating back to a previous approach to the Sun. Rosetta project scientist Matt Taylor says the two studies of the comet's icy content are revealing new details about the composition and history of the nucleus. He says while the flight path of the mission may be over, it's clear that the scientific exploitation of the enormous quantities of data collected by Rosetta will continue for some time. I'm Stuart Gary, and this is SpaceTime. Scientists have come up with a new hypothesis to explain the weirdness of the so-called alien megastructure star. The star, officially named KIC 8462852, has shown dramatic changes in brightness, which until now couldn't be explained by most astrophysical processes. The controversy first began back in October 2015, when astronomers first detected strange erratic variations of up to 22% in light curves emitted by the star. Now, normally, if a planet transits in front of a star, you may wind up with a dip in light of maybe 1%. But 22%, no one has ever seen anything like this before. Previous explanations have included the possibility of swarms of comets surrounding the distant star, debris from a planetary collision in the star's solar system, and viewing a newly forming star and planetary system edge on. One of the best, however, was the now notorious alien megastructure suggestion, which grabbed the interwebs, spreading like wildfire. That all started when Penn State astronomer Jason Wright jokingly postulated that with all the other options gone, maybe it could be an advanced alien civilization harvesting much of the star's energy using a Dyson sphere, a massive structure composed of solar panels large enough to surround an entire star. Now, as I've been stressing, he was joking when he said it. Trouble is, he failed to realize just how dumb some of the tabloids really are. Now, a team from the University of Illinois have come up with a new idea. They're reporting in the journal Physical Review Letters that KIC 8462852's weirdness can best be explained by internal phase transitions. These are causing powerful outbursts on the surface of the star that are occasionally blocking the electromagnetic visible light emissions that would normally be observed by telescopes. Phase transitions involve materials changing states between a solid, liquid, gas, and plasma. The authors reached their conclusions by looking at how the star's large and small dips in brightness related to each other. They claim to have found a statistically significant mathematical model known as avalanche statistics which appear to match the pattern. Avalanche statistics involve patterns of small dips in data happening between larger dips and causing even larger dips to occur in an avalanche-type effect. Avalanche phase transitions are known to occur on the Sun associated with solar flares and geomagnetic storms. The researchers think a similar thing but on a larger scale could be happening on KIC 846285-2 as internal material transitions generating erratic outbursts are blocking out the light. This is SpaceTime. I'm Stuart Gary. NASA's new Cyclone Global Navigation Satellite System CYGNSS has been successfully launched into orbit aboard a Pegasus rocket. The CYGNSS constellation of 8 small satellites will allow scientists to study tropical cyclones, hurricanes and other storms in unprecedented detail. The orbital Pegasus rocket was air-launched from the underbelly of a specially modified Lockheed L-1011 airliner named Stargazer, 40,000 feet above the North Atlantic Ocean, about 160 kilometres off the Florida East Coast. It was a case of third time lucky for mission managers, with the launch having been called off twice previously, once due to a faulty circuit board in the launch deployment system aboard the OCA or orbital carrier aircraft, and then again because extra time was needed to upload and verify the new software. The 17.6 metre long 3-stage winged Pegasus XL rocket is designed to carry payloads of up to 450 kilograms into low Earth orbit.
This is Pegasus Launch Control, T-minus 57 minutes, 45 seconds and counting, less than 1 minute away from the departure of the L-1011.
And launch team, we're now complete our pre-takeoff checklist, currently in our climb cruise checklist.
65 minutes after lifting off from the Cape Canaveral Air Force Base, together with a NASA FA-18 fighter operating as a chase plane, Stargazer released Pegasus over open ocean, allowing it to freefall for 5 seconds before its first stage Orion 50S solid rocket motor ignited for a 77-second burn, taking the spacecraft above most of the atmosphere.
LC Peg is go for launch.
PLT, LC is go for launch. PLT confirm.
LC PLT confirms go for launch.
Drop on my mark. 3, 2,
1. Go for release.
Pegasus is away.
And drop. Pegasus is away.
LC
The
PLT.
ignition of the Pegasus rocket with CYGNSS, helping hurricane forecasters understand and predict the intensity of hurricanes.
Power buses remain nominal, approximately 30 seconds
LC is
into
an
flight.
RCO. First motion time of 13:37:21.
Vehicle is now past max Q.
866.
Attitude remains
That's
nominal.
13:37:21.
30 seconds until stage 1 burnout. Attitude remains nominal. Power buses remain strong. 10 seconds until stage 1 burnout.
All data coming back looks good, getting ready for the first stage to burn out, right on time.
Stage 1 is burned out. Attitude remains nominal.
Main engine cutoff for MECO occurred at an altitude of about 200,000 feet or 61 kilometres, at which time the first stage and Delta wings, which provided some of the lift, are jettisoned, and the second stage Orion 50 solid rocket motors ignited for a 78-second burn.
Coming up on first and second stage separation.
Stage 1 separation and stage 2 ignition. Stage 2 TVC is operating nominally and controlling the flight of the vehicle.
Midway through the second stage flight, the payload fairing splits and falls away, uncovering both the third stage of the launch vehicle and the 8 CYGNSS satellites.
Standing by for fairing separation.
Power buses remain strong. Approximately 20 seconds till fairing deployment.
Second stage flight looks good.
Fairing separation is confirmed. Attitude remains nominal after successful fairing separation. Approximately 20 seconds until stage 2 burnout. Vehicle is flying down the nominal track, indicating good performance. Stage 2 is burned out. Attitude remains nominal. Stage 3 TVC is initiated. Stage 2 separation.
After second stage burnout and jettison, the spacecraft undertook a 4-minute cruise phase before the third stage's Orion 38 solid rocket motor ignited for a 64-second burn. sufficient to take the spacecraft into orbit.
Stage 3 ignition. TVC is operating nominally, following command and controlling the flight of the vehicle. At its nominal during Stage 3 burn.
We've had acquisition through Kourou.
Vehicle systems remain nominal during Stage 3 burn.
A fourth stage is sometimes added to the Pegasus launch system for high altitude, finer altitude accuracy or more complex maneuvers. If it's fitted, the fourth stage uses a liquid-fueled HAPS, or Hydrazine Auxiliary Propulsion System, which uses 3 restartable monopropellant hydrazine thrusters. Once in position, the 8 Cygnus microsatellites were each deployed into a 510-kilometre high orbit, spaced evenly around their orbital plane, providing 45 degrees of angular separation from each other. The 29-kilogram University of Michigan and Southwest Research Institute-built Cygnus satellites each have a lifespan of over 2 years. They're each equipped with a delayed Doppler mapping instrument using a global positioning system receiver and 3 L-band GPS antennae fitted with low-noise amplifiers and a delay mapping receiver processing unit. 2 of the antennae face down towards the planet to pick up GPS signals reflected and scattered by the ocean surface. The third is zenith pointing, upwards to receive signals directly from GPS satellites to determine each Cygnus spacecraft's own position. Scientists will then study the way the GPS signals are scattered by the ocean surface to help them determine wind conditions near the surface. The constellation will make accurate measurements of ocean surface winds in and near a cyclone's inner core, including regions beneath the eye wall and intense inner rain bands that previously could not be measured from space. The frequent detailed measurements of hurricane wind speeds will provide scientists with important indicators as to the storm's strength, ultimately helping improve hurricane or cyclone tracking and intensity forecasts. Each Cygnus will monitor a 25-kilometre wide strip of the Earth's atmosphere spaced several kilometres apart, thereby allowing the constellation to obtain detailed observations of a storm over just a few hours and covering the entire tropics every 7 hours or so. The use of an 8-satellite constellation allows for more frequent observations, allowing for a better characterization of the early stages of a cyclone's formation and the storm's eventual decay. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.